What's the question? Doesn't look like a negative for living. I was looking at the double vision. Yeah, it's good. You're staying with the middle. I thought it was a family of solutions, but I said, okay, if it's okay. But he never used it. It made no sense. You can contact the author. Maybe he will give you like some of the money. You'll be like, oh, thank you so much. No, they usually don't answer. They have a page of errata that stays there for years sometimes. Hi, can you hear me? Can you hear me? No? Oh, yeah, I can hear you. Perfect. Hi. Nice to see you. Are you talking? Good. I mean, I don't know. I mean, all right, fine. One. No? Hi. What? Yes, we talked about it last time. Yeah. Yeah, you even asked me a question about sharp. Remember when you asked me what does sharp mean? Yeah. What? Yeah. The what? No, they're not the same, but like, this is too loud. Um, so, I mean, we'll talk about it a little bit today, but the rate, I mean, there's a bunch of definitions, but the one in the book, right? The one we defined last time, what was it? Wasn't it something like the ratio? I don't know, I forgot. There were so many. What did we have? Um, but anyways, I mean, when you see rate, usually they take x, k, or minus to some global minimum. So in the homework questions, they tell you find this guy, right? And then you do the gradient descent, and this will be some error, right? And that will be the rate, like how far away you are from the minimum. This should be something like 2 minus k, and that's like how fast you're going. It could be like 1 over k, I don't care. But it's how quickly you're going to the minimizer. From this, it's the same thing. You can look at ratios, I don't care. They're all sort of the same. You still need to figure out, this distance. This is the core object. You understand? Yeah? Okay, good. We're not very we're not going to kill you over your understanding of rate. It's just make sure that you compute this guy and you estimate it from above by some error in k, like I don't know, whatever the case may be, right? Is that okay? I'll do now the matrix. All right. So we take you to be any symmetric matrix. We order the eigenvalues lambda 1 to lambda n. Capital lambda is the biggest eigenvalue, and they're all non-negative. I mean, it's positive definite, so in fact they are strictly positive. And we've talked about that because it's positive definite, the Hessian is equal to a positive definite matrix, so it's convex and strictly convex because it's positive definite, not semi-definite. And so you have a unit minimizer that you can find. If anybody remembers linear algebra, symmetric positive definite implies invertible. Can someone tell me very quickly why? Just to see how far your knowledge of linear algebra has gone into your brain. How deep? Because I will use eigenvalues. I just want to see if you like. I want to see the level. Yeah. Yes. Yeah. Perfect. That's all I wanted to hear. So eigenvalues are positive. Then determinant of Q is the product of the eigenvalues, and so it's not zero, so it's invertible. Okay. Good. Fun times. linear algebra. All right. So we can now look at this function, and we'll come back when we go to conjugate gradient. So I might as well talk about it now. This function q of x is not f of x, right? These are not equal. But their first order behavior is, their second order behavior is the same. Okay, so let's see why. So you open it up, and what do you have? You have this guy plus that guy. But then what is qx of star? B. Okay, I don't know if you. So how did we find this? Just to be clear, you find the stationary solution and you set it to 0, right? And so you get q transpose q, but it's symmetric, so you get q of x minus b, right? And then you get your guy. So please remember this formula, all right? We'll use this many times today. All right, so that means you get f plus a constant. This is x star, so it doesn't depend on x, so you get constant, which means what? Which means that q x of q is equal to q x of f, so they have same minimizers. All right, that's a nice trick where you can turn it into quadratic form. All right. Yeah, so they have the same gradient. All right, so we talked about this last time. The steepest descent algorithm is given by xk minus, let me flesh this out. It was ak minus the gradient of, let me write f. Right, so you have xk, and then you move in the direction of most negative decrease. Right, so you move in the minus gradient, starting from xk. And we have a formula for ak. I'm not gonna go over that, but if you remember, it was anyways, I won't do it now, it's too much. Okay, let me remember. So it was gradient of f times, so it was inverse, right? One of these two. Yeah. All right. Because the 1D method is f prime over f double prime, and this guy we had the Hessian times the gradient. All right. Anyhow, the point is, if you do this calculation here, you will get this stuff. All right. Okay. So, and this step might seem confusing, so let me explain. So here we evaluate. So we evaluate q of xk plus 1, which is equal to q of xk minus akg. And then you know what this q is. Q is of the form x minus x star, x minus x star. Okay, so I'm not going to do all these steps. It's going to take us too long because it's just linear algebra. So you plug in this point, xk minus akg, and you can already see you're going to get the qxk by linearity over here for some of the terms, and then this ugly fraction is the cross terms. Okay, so let me do a little bit just to see what's going on. So again, let me repeat. We are trying to find the minimizer of F. And we simplify the question by looking at the minimizer of Q. Okay, so instead of finding the minimizer of this shifted guy, we find the minimizer of this quadratic form because it's nicer, has a more convex structure. So we go for that, step one. Step two, we apply the gradient descent algorithm, which was this one, okay? You move by negative gradient. We had an explicit formula for AK last time when it's quadratic form. So we had this Hessian over here. All right. And now I want to show that Q of xk plus 1 will be strictly less than Q of xk. Okay, so I want to get a rate. I want to show, like you were asking. So I want to compute the ratio or the difference, whatever you like. Yeah, let me say the difference. So I want to compute the difference. What's a better way to say it? Let me say ratio. Yeah. So we're going to compute this, and we will show that it goes to 1. With what speed, what rate? All right. So we're going to need a famous inequality. We're not going to prove it because it will take us too long. But you can just memorize it. It almost looks like Cauchy-Schwarz. So it is Cauchy-Schwarz. You might ask me, what is Cauchy-Schwarz? So we talked about it a long time ago. So let me talk about it quickly here, just to see where this came from. So Cauchy-Schwarz says, you give me the dot product of two vectors. They're equal than the norm squared. So, okay, that's Cauchy-Schwarz. But it turns out to be vastly more general. You can take any inner product and you still have the same sort of formula. And if you remember from, so this H means inner product. So if 2 to 4 is a prerequisite, isn't it? Yeah, okay, perfect. So I have free range. I remember this, we did this in class. So inner product, we define it for matrices, right? And this is the one we're using here. So QUV. Okay? So this defines an inner product, and this Kantorovich inequality, as you can see here are your guys. You just use Cauchy-Schwarz to this one. Okay, it's a little bit of work, so I'm not going to do it here, but I just want to tell you what the intuition is. All right, good. I can, yeah, let me rearrange it for you a little bit. I have what? So, okay, what am I thinking? No, you're definitely right. There is no, yes, thank you. I don't know what I'm thinking, yes. Let me move it around. Anyways, it's too much. Okay, so this is the inequality, and why is it beautiful? It relates the matrix to its to its eigenvalues. Okay, so here's the eigenvalue lambda, the top and the smallest one. So where was it? Over here. So lambda small is the smallest, lambda capital is the biggest. Okay, so this is largest, smallest. Anyway, so let's apply it just to see what the hell is going on with this. Just to see. All right. So yeah, right. There's a whole there. We're going to prove right. So I'm going to show you that the speed with which you converge is given by this. Okay. So that means, so what do I want to say? Oh, yeah, we'll do it. I have a bunch of results. So let's start. First, I will give you this. So this is called order of, not order. We have a bunch of names for this. But yeah, this is your rate. So I'll do it next. All right, first I have to prove this inequality. So we just had this from before, just the gradient descent step. And it was beautiful because it's exactly the left-hand side of Kantorovich. So is there a way to extract this? No? Be nice. All right. So yeah, V will be GXK. So you apply it for this V, and you get a bound in terms of eigenvalues of Q. Okay, so again, lambda is lambda 1, capital lambda is lambda n, smallest and largest eigenvalue of Q. All right. Good. And of course, you're free to use this. So if I give you some, if we give you some matrix system, you just have to find the eigenvalues. All right. So yeah, then yeah, you just rearrange and you get your inequality. All right, so now let's put this to use. So now we just show that, where is R? Yeah, so we have this lambda, all right. So R is equal to lambda minus over lambda. And this guy is less than 1. Can someone tell me why? Just to see if you understand. It's obvious, huh? Yeah, this guy is bigger than this, yeah. And they're both positive. So that's why you can divide. Yeah, so you do that, and this is your R. This is what's called rate, okay? And as you can see, as you take its power to the K, what will happen is this guy will go to 0, right? Is that okay? So let me go back to what Q was, since that's of interest. So as you can see here, yeah, you, where is it? Over here, yeah. So it says that when it hits the minimizer, this guy over here goes to 0. Okay, as x goes to x star. Okay, and it gives you the speed. It tells you that it goes to 0 with speed r to the k. So, right, so let me give you the order of convergence. Okay, so I will prove this. I will prove this next, but let me apply the previous. So we just showed that this ratio, it's less or equal than this. I don't know why I wrote equal. Right. So what do I say? Right. So yeah, and this guy over here is less than 1. That's what I wanted to say. So call this, I don't know, we called it C, right? So what we were doing, we were taking a limit in xk, right? Yeah. And this xk would just be bounded by this constant c, which we call the rate. So this is called the rate. And this exponent is called the order. Is that okay? Yeah. All right. And so, I mean, you can use this, right? I don't expect you to sit down in the quiz and derive this. So if your guy is a matrix, find the eigenvalues, okay? And just plug it in. That's not hard. Yes. Yeah. To use for what? I mean, all right, how do I say this? There's no like, when we say rate. Okay, anyways, I mean, yeah, the one I just mentioned over here. Yes. Oops. But they both tell you how fast you're going. It's not really like, but yeah, this one, yes. Yeah. All right. Yeah, so this is the rate of convergence. And what else did I want to say? Yeah, I can, anyhow. So I'm going to prove you this rate, okay? So I'm going to show you that this ratio goes to 0 with this speed. So I mean, going back to your homework, right? Because you might be, if you can write your guy as a matrix, I know you have a bunch of polynomials, but if you can write as a matrix, then boom, boom, and you're done. Okay, good. All right, let's prove this. Yeah, so for matrices, this is the smallest eigenvalue, this is the biggest. And so you have this inequality. It's actually hard to prove, and I did it in class, but I'll leave this to you. You have to use the spectral theorem. So there's a little bit of work. Can you see it right away? Huh? Like how to get these inequalities. Yeah, you guys can think about it. It's a cool question. Requires linear algebra. All right. So going back to our guy, this was Q, and you have the following bounds from this result from here. So we use the first one over here, and we use the second one over here. Too many arrows, I hate that. So it's like this and like this. And why do I do this? Because I want to study the ratio of this guy and that guy. So let's do that. So again, where am I there? So this guy, you have a upper bound in terms of qxk plus 1. So you do that. And the other guy, you have a lower bound, so it becomes an upper bound when you take reciprocal. All right. And so you get the ratio of eigenvalues as requested. And yeah. And then we already computed this guy. It was
So we had square root of, no, there was no square root. Lambda minus lambda, lambda plus lambda, right? Good. So that's your rate, because this guy is less than 1. So as you take successive powers, it goes to it goes to 0. What else? Sure. Right. What shall I say? All right, yeah. So in Newton's method, we had this annoying part. If you remember, I had this Hessian matrix, and it made my life really hard. But in a way, we again have to compute. Here, you don't have to compute the Hessian. So let me add this. But here, we already know. But here, we already know that the Hessian of this guy is Q. So don't take this too much to heart. But it is true. For gradient descent, you don't need C2. So let me remind you once again, this guy requires C3, this guy requires C1. All right. Can we find an upper bound for the order of convergence? Upper bound. Why would you want an upper bound? What? Right, yeah, lower bound, yes, that's the sharp things he was talking about more. But yeah, like here you, one is, you know, that's the sharpest. How shall I say this? Yeah, let me, because this is a good question. So suppose you put some other power. So xk plus 1 minus x star over xk minus x star to some a, and then compare it to same stuff, but to some b. And so this is a limit, call it C alpha, and this is another limit, call it CB. And what's the reasonable thing to do? Let's take the ratio. So look at the limit of xk to the b over to the a. And let's take b bigger than a. So this is b minus a, so it goes to 0. But then what is this ratio? So this ratio is C alpha over C beta, right? So since it goes to 0, it's not as, since this is 0, it means that C alpha, it's much smaller than CB. So C alpha is a better approximation. So the smallest one is what you want, right? So do you understand? Andrew, is that okay? If it's, no, I mean it is, but you don't want that. You want to get the sharpest, right? Like, okay, let me say it this way. Suppose you have it, and you have just to the 1, and then you already know that this goes to something finite. But then if you multiply by something bigger, like 1 plus b, this guy goes to infinity, right? So no. Is that okay? I mean, that's the definition, that this limit exists. But if you increase by a little bit, it will blow up. Andrew? Okay, I don't know. Okay, good. Do you understand? Andrew understands, but I'm not sure. Anyways, the point is always go for the smallest power, all right? So that's what they mean by sharp. Meaning that if you add a little bit more, it has to blow up. Okay? Of course, you can put smaller powers, but you cannot put bigger powers without risking a blow up. Okay? So of course you can multiply on the top by a little bit more, right? Because this guy will go to the constant and this guy will go to 0, which is okay. I don't know if you follow. Okay, his question was, let me phrase his question for the people. His question was, suppose you know that the limit like this to some power a is a constant. Can you also say the same for b bigger than a? Yes or no? No. And the reason is, suppose you start from there. Okay. And now, so start with this b, split it, a, b minus a. Is that okay? And now, product of limits is limit of products. First guy goes to C, second guy blows up. Okay? All right, good. Are you good? All right. So no, always go for the smallest. Okay, the sharpest. You can't go too small. Go for the one you're allowed to. You can't go too big. Yes. All right, anyhow. Okay, so again, because you might be asking me, what's the rate? What's the rate? The rate is there's many ways to do this, but the one in the book is you compute this ratio and you're trying to find some R going to 0. So it will be like some CR and R is less than 1. All right. Okay, questions? All right. It turns out there's an even faster method, perfect for quadratic matrices like the one we just did. And it's faster than first descent. And in real applications, you mostly are dealing with matrices anyhow. Like, I mean, nobody studies sine of x. Like, you usually have some regression model, right? Some covariance matrix, and you're trying to find the minimizers. So people have found faster methods because gradient descent is a general tool, but there are more specific ones, and this is one of the more famous ones. So let's do it. Again, we're going to study quadratic systems. And this is cool because if you have f being C2, then we have the following approximation. F is equal to f of x0, initial guess, plus the gradient of f at x0 plus the, can I write this as v? This is exhausting. V, and then, well, I need C, no, let me call it theta, x of theta. Let me call it theta. At least for some theta, linear multiple of x and 1 minus x0. Right, so this is our mean value theorem, and oops. But we also had the Taylor expansion, so you can also write this same stuff, but then put an error in V cube. Well, it's cube, no, it's squared, it's fine. If you can allow me to have C3. Anyways, what's the point of this? The point of this is when you're very close to the minimizer, all that matters are the first three terms. Okay, when you're like close to the minimizer and you have an OV square error, where we already talked about gradient descent converges in squared order, so you're good. You're not missing out much. Okay, so really, the problem reduces to minimizing functions of that form. Okay, good. Where Q will be the Hessian of your nonlinear function. Great. All right. So now we're going to go into linear algebra. Okay. So we need the following concept of orthogonal vectors. So again, going back to 2 to 4, the intuition here is define inner product space Rn with Q matrix, and this is the U, so this is U QV, okay? And all we're doing is we're finding the basis for this vector space. Okay? That's the game we're playing here. So that's all that means. Because if you remember, orthonormality gives you independence and it gives you the basis as well. All right? So you just need this. All right. So yeah, so these are the vectors. We need yeah, anyway, so this is the vectors. Okay, let's do some examples. If Q is the identity matrix in Rn, can someone tell me what this condition means? So the QD prime Q. What's the translation of this? And it is. Yeah, so but why is that? So suppose you have a vector and you have a bunch of ones. It's the identity matrix. So this guy gives you back D prime. And so, all right. And can someone tell me some vectors that satisfy this? What's an example of n vectors? What? No, an example of vectors that are orthonormal. What? What vectors are orthonormal? Like the classical standard basis, right? Yeah. So 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, and so on. right? Is that okay? Good memories? No. So yeah, these are the guys, and anyway, so this is the example you should have in mind. It's the simplest. Another beautiful one are eigenvectors. Okay, that's where the speckle theorem comes from. Is that if two eigenvectors come from distinct eigenvalues, so let me prove that they're orthogonal. So let me do it here. So take, what is this? I'll do it on the side. So suppose QD is lambda D, and QD prime is lambda prime. I don't like this. I'll put tilde like this. All right. So we have QD Q tilde, and this is D lambda tilde D tilde. All right. So this is lambda tilde D tilde. But then you also have the same thing, right? So that's why I do this. Because it's symmetric. So I can write this as QD transpose transpose. Okay? I know it's a little bit messy, but that's the point. And this gives you lambda of D tilde, but they're both equal. So you get, so they're both equal, so you get lambda D tilde equal to lambda tilde D tilde, and you have lambda minus lambda tilde is equal to 0, but this guy is not 0. Yeah, so you get this guy. Okay, so eigenvectors are orthogonal. This was a short review from 2 to 4, but I had to do it because we're going to use this all over the place. Okay. Okay, good. Now, yeah, let's do an example. So here's a matrix, and here's a direction. So when they ask you find the Q orthogonal, all they're asking for is to solve this system. And so I computed this. I computed this time times this. So this case just 1, 2, 3, 4 times 1, 0. So you see, you just where am I? Yeah. What am I doing? I have no idea. This is not right. This is 1, 2. Wait. Yeah, 1, 2, and 3. Yeah, this is 1, 3. I don't know where I'm getting this. Okay, good. So then I will solve it on the side. So I want AB dotted with 1, 3 to be 0. So I want A minus 3B to plus to be 0. So I have a whole family of them. So I get A equal to minus 3B. So, oh, I see how, damn it. So a particular choice is exactly that one. It's the, so D prime, you can just take it to be 1 minus 3. Okay? Is that okay? All right. Yeah, whatever. Okay, so yeah, I have to give you existence, but this is obvious. I mean, this is spectral theorem, but let's talk about it. So if it's symmetric, there exists, and there exists, it's 2 months of work in a course, spectral theorem. Okay, there's a lot of meat there of there exists this basis, but you have it. And I just talked about that, yeah, so I'm just repeating the proof. Yeah, that they form, that they're orthonormal. All right. Let's finally go to the method. Oh, and then again, I'm fine, whatever. So this is a review from linear algebra that I have to do so that you remember. Eigenvectors are linearly independent, okay? If they have distinct eigenvalues, they're linearly independent, so let's just do it. So we want to show that if you give me coefficients, and you can write your guys as a linear combination, the coefficients are over zero. If it wasn't, you will have linear dependence, okay? So this was the definition of linear independence. All right, all right. Oh, here's a mess. Fine, so we do the following dirty trick. I want to isolate AI. Why is that? Because I know that DI, QDI is equal to lambda I, which is strictly positive. Okay, so again, I multiply this by Q because I know it's zero. But the only reason I do it is because I know the eigenvalue is strictly positive by positive definite. So we do that. And so I end up with this, okay? But like I just talked about, the first guy over here is lambda I, which is strictly positive. Okay, so what do you get? Yeah, you get this guy 0 for all I 1 to n. Okay, so you have independence. Good. Yeah. All right, finally, let's talk about the method. So, yeah, and then we'll take a break. So when you want to minimize this, I think we made it clear that when you take its gradient of this guy, call it f, you end up with a q of x minus b. So when you set this to 0, you get that the minimizer is this inverse. Okay. So then the name of the game is to find it, to approximate it. All right. So let's do that. So yeah, we start with our collection. We just proved that they exist using a spectral theorem. So we got this with spectral theorem. And now here's the beauty of this method is that you know what the minimizer is, okay? Gradient descent, you have no idea. But here you know it already in a way, because once you find your eigenvectors, they form a basis. Okay, you live in Rn, you don't live in like infinite dimensional spaces, like in 2 months from now, a week from now. So the game reduces to find the AI. Okay, so finding X star gets reduced to find the coefficients. And this is an n-step problem. Okay, this is way easier than what we did with gradients, where you had to like explore the whole landscape. Here, we will do it so that you just have to find the coefficients, and that will be it. Yeah, so we want to find the AI. And how do you do that? Like before, when I take the dot product, by orthogonality, what do I know? I have AI, DI, di plus a bunch of zeros, right? By orthogonality. Okay. All right. So then this is your area. This is the coefficient you are looking for. All right. Okay, I'll do the simulation after. So let's take a break. Oh.
Uh, oh, it is different. I don't know if it's right, I mean, but the method, yeah. Yeah, but the numbers I have no idea, yeah.
All right. What will I do here? Yeah, let me do it left. So first, let me describe the method, and we'll do a simulation. So yeah, finding the vectors is easy, because you just have to find the eigenvalues, and you do like a Gram-Schmidt to make them orthogonal, right? Good memories. And what's the method? It's very similar to gradient descent in that you add an increment over here. So this is xk minus, how shall I write? Yeah, whatever. Let me write this way. Let me remove this and call it Q. No, I'll write it this way. This is better. Qxk minus b dk, like this. All right. Anyhow, I mean, we'll explain all this stuff, but the intuition here is, why do you think this goes to zero? The Qxk minus b. The answer is very simple. I just want to learn. Like supposing that this converges to the minimizer, why should this go to zero? Yeah. So Q of XR was B. Yeah. And so that's the intuition of this method, is that we know what the minimizer is, how it should look like. So I might as well use that, right? I don't know what X star is, but I know it close enough. And sometimes you can't even find inverse, right? I mean, so it's not like you can just invert the matrix. And we talked about this. Inversion is very expensive, because you have to compute nonlinear functions. If you remember, we had this 1 over determinant, right? Anyhow, but that's the point. This method is perfect for quadratic functions, and it's good enough when you can Taylor expand up to a second order. Okay. Good. So then we will show that this step process converges to the minimum in n steps. All right. Can I simulate now? So first I'm gonna do, what's the function? Yeah. So I take my A to be this matrix. Okay. 5, 2, 3, 2, 3. And my B to be this minus 2, 4. And now I'm going to do gradient descent. Okay, so shall I zoom in? No. Yeah, so I start from some point, gradient points down. I repeat from the other step. The gradient decreases now this way, and then zoom in. Too much. Okay, this one. Okay, so we made first step. Then the second step, again, remember we were minimizing the jump over this hyperplane. We had this minimum of S, if you remember. And then we repeat. I mean, this is even smaller. Why does it flip? Jesus. All right, anyhow, and then I want to zoom in. There we go. I don't like this software when it comes to this. So hard to see. I give up. You keep running it, and it converts it in 9 steps to the minimizer. Takes too long. Here's the faster way. So this is again same matrix. Okay, I'm not. Where's the matrix? This one. So same matrix, 5 to 3 minus to 4. And let's run it. No, refresh, close everything. All right. So yeah, first step. So this hyperplane, we're going to talk about it, but so you have a black dot. This is your initial point. Okay. And then this hyperplane is the D0. We have some eigenvectors, right? D0, D1, D2, and so on. But here is 2D. So we will prove you what the numerics tell you, that it will converge to the minimizer in 2 steps, because this is 2D. Okay? It took us 9 steps. It was going like this. This guy will go in 2 from theory and practice. Okay? So this is, so yeah, it does the first step, and then it goes along the D1. Okay? All right. And it converged. So you found the same local minimum in 2 iterations. And that's the upper bound. Okay? So if your space is R4, it will go at most 4 steps. Gradient descent, it took 9 steps. Okay, good. And again, let me remind you why this method is superior, is because we know what we're looking for. We're only looking for these n numbers. That's all. I'm not looking for some generic point. I only have to find these n numbers, right? So that makes it way, way, way easier. Okay. All right. Let's prove it. So n steps. Yeah. So let me explain the spirit of the proof. So again, the goal is to find these coefficients given any initial point. Okay, so the goal is find AI prime starting from any x0, which is madness. I mean, if you remember in Newton's method, you have to be like very, very careful on your initial point. Here it plays no role. And the reason is because your domain is very convex-like. In Newton's method, you had the problem of having flat places, right? So that's one of the reasons. All right, let's go. Yeah, so the whole game, the strategy is to prove you that these AI primes are given by these AIs. And once I do that, it tells you that to find the minimizer, I just have to compute these numbers. Okay. So again, please note, there is no X star in AK, right? There's no X star here. Okay. Here there is X star. Okay. So in theory, these A primes depend on X star. We will prove that it doesn't matter. Okay, so here then, again, this guy depends on X star. This guy do not. Okay. All right, let's do it. Because a priori you don't know the minimizer. If we knew the minimizer, why do this numerics? It's pointless. So we're gonna prove that you don't have to know the minimizer. All right, let's go. Same game as before. Because I know the orthogonality. Do I do it here? Okay, let me do it again. So I know the orthogonality, so I have di, AI, di, and then a bunch of zeros, right? Right? Because of orthogonality. Good. Then you isolate for AI and you get this guy. I mean for AI prime, sorry. AI prime. AI prime. And I'm going to prove to you that this is nothing but AI. Okay? Because again, this guy depends on X star, clearly. There's an X star over there. This guy does not. Okay? Okay, good. Let's go. So we had this, yeah, let me give you the, so I should give you, yeah, let me write it down here. Okay, so how do I get this step? Xk plus 1 is equal to xk plus ak dk. Do the previous one, so xk minus 1, ak minus 1, dk minus 1, right? And you keep doing this, and you get this guy. Okay, good. All right, so same game, nothing different. I'm using orthogonality because I want to isolate AK, all right? So I isolate AK and then have dk plus 0. Oh, no. Oh, sorry. But there is no such term. So this is always 0 because dk is orthogonal to all the di or I less than k minus 1. Yeah, good. I should pay attention. All right, anyways, what's the point of this? So again, I want to show that this AK prime is equal to AK once again. All right. And what did we do here? I know that this guy is 0, so this guy is 0. So then I can just add it over here. I can do minus 0. Okay, so remember, A prime K, what is it? It's given by this. Okay, and then I just add the 0. All right, and why do we do this? So with a sleight of hand, x0 disappeared. And that's the magic of this method, why people really like it. So now there's no x0, which means the initial guess can be anything. Can be any number. Okay, and this is the step in the proof where that happened. And okay, but now we know that, where is it? Here. We know that Q of X star is B. So I put the B here, okay? But this guy over here was just the definition of the AKs. This was just the definition of them. All right. So that's the result we want. So let me review what just happened. We want to show that this algorithm with these steps converges to the minimizer, which is given by, if it's, it's given by QX star equal B, but we don't want to invert because it costs. So we want to show that it will go to this X star solution in n steps. So we start with X star and we represent it in the D vectors. And by doing that, we get a formula for the AI primes. So we get a formula for X star. And then we use the trick that successive steps have this orthogonality property. So, yeah. So, and we're going to use this later, so I might as well talk about it here. So if you remember in the picture, in the simulation, the hyperplanes were orthogonal, if you remember a little bit. And this is shown here. So the new direction is perpendicular, is Q orthogonal to the XK step. So suppose this is XK, this would be a DK, okay? But this is not 90 degrees. This is, we mean orthogonal in the Q, okay? So it's a little bit hard to visualize because Q is so generic, but that's the main idea. And I'll come back to this because this is the heart of the method. All right, what else? Yeah, so I started with X0, remember? So I started with X star minus X0 given by A0 prime D0, AN minus 1 prime DN. And I showed that in fact, these are just the usual coefficients of conjugate descent or conjugate directions. Okay. So that's the beauty of this method. X0 is irrelevant and X star naturally got encoded. Good. All right. Yeah, so for this, you just need to compute n steps, all right? And why n steps? Because you have n coefficients. So you just need to move d0 to dn times. All right. Okay, any questions? If you have questions, you can just tell me. So now let's go into the intuition of conjugate directions. It's a bit hard to visualize. Gradient descent is easy. We talked about it since the beginning of the course, that it points normal to the level sets. And something similar is happening here. So let's talk about it. We proved a long time ago that when you have a convex function and you know its gradient is non-negative. So remember, like Yumin was asking, so this is on the boundary, right? And interior, but inside you want equal, right? Okay, we talked about this, right? So a local minimum satisfies this condition because locally it says that the gradient is pointing up. That's all. Right. What shall I say here? Yeah, so now Hyperplane, yes. So what do I want to say? Yeah, so the hyperplane is given by all points V in Rn that are of the form V equal to Y minus X naught. Okay, for Y also in Rn. Okay, I mean in 1D, this is just saying it's a line with an intercept. And it crosses the origin. Yeah. All right. What else? Sure. So then if you do it both ways, let me do it here. So this is supposed to be like this. Then y is minus z in the hyperplane. Let me show you why. So minus z is equal to, no, z is equal to minus x naught. And how shall I say this? Oh, let me deal with normal vectors. Yeah, so another definition of this guy is all the vectors in Rn that are dotted equal to 0 with n. Yeah, let me do it this way. It's a little bit nicer. So then indeed, if z dotted n is 0, then minus z dot n is also 0. So you do it this way, and you get this. All right, so what's the point of this? The point is you have this perpendicular condition, right? So yeah, anyway, so in the case of omega being a hyperplane, okay, and the one I like the most is that you can write it as you know, what do you call it? V dot n equaling to 0. Okay, I think that's the easiest, right? Because it just says you have some guy and some plane, and everybody is normal to this plane. So in this very specific case, if you want to find the minimizer, you just have to find the x naught who is normal to the hyperplane. Okay? And pictorially, it says something very stupid. It just says, this is omega, and then take, take the parabolic guy. This guy here is the minimizer because it's normal, right? So take x squared plus y squared. This is the y, this is the x. So over omega, you just look at the 0, 0. And this guy is normal to this plane. Okay? All right, good. So now we talked about this to give you some intuition of the conjugate directions, because it's very counterintuitive at first. So if you remember a bit of 2 to 4, this is called nilpotent. So you have a increasing eigenspaces. So this is E1, right? Your first eigenspace. And then second guy is E1. Yeah, okay, let me write this way. Span of, no, I'll write the summation. E1 plus E2. All the way to E1, EK minus 1. And the direct sum gives you the space. Okay? So that's spectral theorem. All right? Okay, good. And yeah, in case you don't remember, EI just means take all the V in Rn so that Q of V is equal lambda IV. Okay? Good. All right. So we're going to prove the following result that the one from the simulation, which let me run it again just to show you what's happening. So this hyperplane that you see here, this hyperplane, this is E1. Okay, this is the span of the first eigenvector. And you see when I do the next step, it's orthogonal to it. Okay, again, this is spectral theorem. It says that eigenspaces are orthogonal to each other. They form a direct sum. Okay, that's all this picture is saying, and I'm just going to prove it mathematically. All right. Yes. All right. So from what we just talked about from before, we just showed that this is true, right? The gradient is normal to this hyperplane, okay? And again, the idea was you start with this condition, but then apply it for y minus x naught in a hyperplane. And yeah, and you get this condition. Now the hyperplane here would just be, I know it's a kind of weird way to write it. So this, yeah, this is the hyperplane. Yeah, all right. What's next? Right, and our F is this guy, yes. All right, so again, what am I proving? Let me explain it on the side. So in the simulation that we just did, what happens? You start with x0, you draw, you have this hyperplane, x0 plus b1, and then you're trying to figure out the direction. You're trying to find the next step, because again, you don't want to sit down and find the d directions. So there's an easier way, okay? So it will be, so you have your, let me do it in like this. Let me draw it like this, and let me take a slice like that. Okay, good. And then put x0 over here. You're supposed to think about this as 3D, okay? And this is a slice that you took, and this is the hyperplane x0 plus b1. Now along this slice, you're minimizing f, and it will get minimized over here, okay? And you call this guy x1. Then on the next step, you move the other way. So you go like, it was like this, but now you take it like this. And you play this game again. You find the x2 guy. Okay? All right, so I'm going to prove you that this is what conjugate direction does. Each time it finds a plane and minimizes. All right. Okay. Yeah, anyhow. So I have to prove this for all k starting from 0 and then all the way to n minus 1. When you put k equals 0, you get gradient of x 0 is equal to, where am I? Yeah, so this is equal to q of x0 minus b, which we call it g0. And we're asking for this guy to be normal to b0. But by definition, we had this to be empty. So it's kind of stupid, but it is what it is. All right. Now, induction hypothesis. Our induction hypothesis is the following. So, so here assume that, what is it, GK dotted with a guy from BK. So again, BK was the span from D0 all the way to DK, right? Okay, -1, fine. DK -1. So we're saying take a vector from there. Yeah, plus x0, fine. Where V is of the form A0, D0, blah, 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 AK -1, DK -1. All right. So this is your inductive hypothesis, and I'm going to prove, want to show that GK plus 1 dotted with x0 plus VK plus 1. So take VK plus 1 from BK plus 1. The span of up to DK eigenvectors. All right. So again, why are we doing this stuff? To motivate that indeed the algorithm converges. Okay, and because it's not obvious. All right. Okay, so I have to show you that this guy is 0. Okay, so I want to show that this guy is 0. Okay, good. Is it clear? Okay, yeah, let me ask you. Why if I show this, I'm done? Just to say, it's a linear algebra question. It's not from this stuff. Why if I show this, we're done? What do you think? You see, the induction is this, right? VK plus 1 from this span of D0 all the way to DK. So how are we, yeah, you're almost there. So what will be the, so let me say it this way. This is a linear algebra question, okay? Because I want to make sure you follow. So take a vector space spanned by, U0 to U, I don't care, M. And suppose you want to show that G with a generic element in here is 0, okay? What's an easy way to show this? What? What do you think? How would you do it? Okay, pretend I'm Homer Junior, whoever your prof was. This is 224. Welcome back. So how do I show that this is equal to 0? What will I? What's the easiest way? Just throw a guess. What's your guess? Huh? G will be what? Oh, no, I'm saying, like, forget what we're doing, just here. Okay, maybe I'm making it, you just have to show that it's 0 with each one of them. Because every V is a linear combination of these guys. Is that okay? That's all. There's nothing else. And like Bill really said, we already have the first K minus 1 steps by induction. So we just have to check the last guy. Okay, all right. Okay. So, good. But we have a formula for it. So, where was it? Yeah, let me do it here. So we had xk plus 1 is equal to xk plus ak dk plus 1, right? Right? Okay, I forget. What was the algorithm? I think it was dk. Yeah, dk, good. All right. And then you evaluate it on this guy. So you have q of xk plus 1 minus b. So this is the gk plus 1. And let me do the calculation here. So this is q of xk plus plus what? Plus q of dk minus b. Okay. All right, good. And this guy and this guy are gk. So that's how you get all that stuff. All right. Good. So that's how you get this expression. And then, oh yeah, I plug in what my AK is. So this guy is AK. And now I use induction. So by induction, where is it? No, this is easier than that. So here we have the following cancellation. So this guy cancels out with this. And so you're left with dgk minus dkgk, which is 0. Okay. So again, and like Ben Rui said, induction was used to get the gk plus 1 dotted with dm for m less than or equal than k minus 1. Let me write this clearly here. So, and inductive hypothesis, we have dm gk plus 1 is equal to dm gk plus a dm q dk. And can someone tell me why this is 0? Can you read it? So why is the first term 0? Because of what? The what? Can you speak up? Yeah. And what about the second term? What do you guys think? Yeah, beautiful. Good job. So the second guy is by Q orthogonality. Okay, so that's how we use the induction and the uh, orthogonality. All right, good so far. Let's keep going. All right, go over the, okay, fine. So yeah, for the ones less than it, uh, like we just talked about, this guy is 0, so this guy is dead. And here we use orthogonality. Right. So let's see. Let me go back to the theorem. Okay, just to see if you understand what has happened. So minimizer, finding the minimizer. So xk is a minimizer on omega given by x naught plus bk if and only if what? What's the condition we talked about? Do you remember? Yeah, let me talk about it. So it was if and only if the gradient of f at that point xk times v is equal to 0 for all v in omega. Okay? So this is the thing we talked about up here. Okay? So if you have orthogonality at this point, you have global minimum. All right? Is that okay? Okay, good. So that means by proving this result that where is it? Over here. By proving this result that you have the gradient being normal to this hyperplane, you obtain that xk is the minimizer of f on omega given by x0 plus bk. You understand? So in other words, going back to the pictures, here's what happens. So we drew this plane, x0 plus b1, and the function does something like this. This is the x0. So if you like the f of x0, and this guy here is the f of x1. Okay? So this method proves that f of x1 is smaller than f of x0 because it's precisely the minimizer. Is that okay? Do you understand? Okay, good. So that's why this method converges to the minimizer. I mean, it's a complicated method, but it's the fastest for these quadratics. It goes in n steps. I mean, it's amazing. So it's just bounded by your dimension. All right. Right. Yeah, but the name of the game now is you have to find these vectors. So you turn an optimization problem to a linear algebra problem. But for that, we have amazing methods from the like 1600s. Gauss has been working on this for a long time. So we know how to find this. We have many quick methods. So again, the question is find the minimum of this quadratic. And we have this algorithm. Anyways, and then what we just proved is that if you just take n steps, you converge to the minimizer. It's just n steps. Gradient descent can take infinitely many steps. For example, if it encounters a valley, you're done. Okay? Gradient descent will just get trapped over here. But this method will just, it doesn't care. It's not looking at greatest increase or decrease. It's looking along this eigenvectors. Okay. Again, this is not a gradient of f of xk. That's not it, right? So it overcomes local traps, which is a big problem in optimization. Huge. Okay. So what else? Yeah, so I mean, going back to that simulation just for a second. It's a nice simulation. Yeah. Nope. So let me, how can I do it? Can I zoom in? I want to show you the slice. It's kind of hard to do it. All right, I'll do it this way. Yes. Like a boat. I don't know if you can see this, but like there's a hyperplane and all the method does is it follows um, along this slice. Okay. So the conjugate gradient finds the minimizer along this slice. That's why it's so quick, because this guy is symmetric. So he finds it right away. Okay, all right, good. Because if you take any slice, let me say it this way, if you take any slice, their minimizer is the same. I mean, close enough, okay, whatever. All right, very good. Because the hyperplane is supposed to cross the origin, and the origin is the minimizer. Okay, good. Yeah, so the result we just proved is that at each step, we have this minimization. Because this guy is in the x0 plus b1, but this guy is also in here, right? And we just show that q of x1 is equal to the minimum over v in x0 plus b1. But then this is less or equal than q of x0. Okay, that's the method. There's nothing mysterious about this. All right. Yeah. And get close to the minimizer. And this method is beautiful because you know that it will converge in n steps. Gradient descent does not guarantee that. Do I have time? How big is this? No, I want to do it slow next time. Okay. So I'll do it on Thursday. Thank you.